Welcome to this class. So today we start with the model analysis in fluid mechanics. In order to know about the performance of the hydraulic structures, example dams, spillways, etc., or hydraulic machines like turbines, pumps, etc. Before actually constructing or manufacturing them, their models are made and tested to get the required information. So before constructing these big structures, we have to manufacture their models and tested to get the required information. The model is the small scale replica of the actual structure or machine. The actual structure or machine is called prototype. The models are not always smaller than the prototype. In some cases, a model may be even larger or of the same size as prototype. Depends upon the need and purpose. So, if you want to create a aeroplane means what we have to do is first we have to construct a model with some scale. Okay, some scale means it doesn't in the exact size. So we will 3D print this and then we will place this one inside the wind tunnels and then we will find out the drag force and the lift force uh, for particular wind velocities. Then with the results from this model, we will go for the prototype, then product. Okay, so this is the general procedure for all the kinds of products. So to reduce the cost, if, for example, if I want to produce a pump, means first I have to model it and then I have to analyze the flow inside the pump and then we will go for the prototype. After that only I will go for the product. So that's the sequence. So for that we must understand the model analysis and then how to do the model analysis. So today we will discuss about this thing. So next slide. So advantages of the model testing. So first advantage of the model testing is that the model tests are quite economical and convenient. Why these are economical and convenient? So because if I have an idea, that idea related with the fluid mechanics product, so if I directly manufacture that product means if it is failure means it will be cost lots. So that I will go for the model, then I will go for the prototype. After that only I will go for the product. So that's why we will tell that this is economical and then convenient one. So next advantage is that with the use of these models, the performance of hydraulic structures, hydraulic machines can be predicted in advance. So before the manufacturing of the exact product, we can able to understand the performance of the hydraulic structures or hydraulic machines like pumps, turbines, whatever. So then third advantage is that while designing a particular portion of the structure, if clear-cut analytical and reliable method is not available, then in such cases it becomes absolutely necessary to know about the safety and reliability of such parts, which is possible by means of the model testing. Then fourth one is the model testing can be used to detect and rectify the defects of an existing structure which is not functioning properly. So we can able to rectify the defects of an existing structure which is not functioning properly. So we can able to study the existing structure with the help of model testing. Okay. So next slide. The application of the model testing. The first application is from civil engineering structures such as dams, spillways, wires, and canals. So these terms, if you studied about the hydraulic power generation, you can able to know these terms. The next one, flood control, investigation of silting and score in rivers, irrigation channels, then turbines, pumps, and compressors, design of harbors. So in oceanography, design of harbors, ships, and submarines are doing with the help of the model testing. So in Tamil Nadu also, in IIT Madras, the oceanography department having the 70-meter sea-like structure as well as 100-meter sea-like structures they have. So with the help of that, they have modeled their products like submarines and then boats, and then they have tested in that. Labs itself, then they will get for some conclusion. The next aeroplanes, rockets, and missiles. Then tall buildings. So in so many US universities, they are designing their university in CFD modeling. Then they will analyze what is the flow around their buildings. So those things are done with the help of this model testing. Then next we will go on to the similitude. So, what is similitude? To find solutions to numerous complicated problems in hydraulic engineering and fluid mechanics model studies are usually conducted. In order that results obtained in the model studies represent the behavior of prototype, the following three similarities must be ensured between the model and the prototype. So in product development, the first process is the modeling and the next the prototype. So if the three similarities should be ensured before it will be converted into the product. So first similarity is the geometric similarity, the next one is the kinematic similarity, the next one is the dynamic similarity. So we will discuss one by one in this lecture. So first one, geometric similarity. So in geometric similarity, for geometric similarity to exist between the model and the prototype, the ratios of the corresponding lengths in the model and in the prototype must be same, and the included angles between two corresponding sides must be the same. Models which are not geometrically similar are known as the geometrically distorted models. Okay, so we will see about the distorted models in the upcoming slides. So let us take LM will be the length of the model, HM will be the height of the model, and DM will be the diameter of the model, and AM will be the area of the model, and then VM will be the volume of the model. So likewise, we will change the suffix P, suffix M with P. So LP, BP, HP, DP, AP, and VP are the length of the prototype, and then H will be the height of the prototype, and DH will be the diameter of the prototype, and then AP will be the area of the prototype, and VP will be the volume of the prototype. So VM and then BH is the breadth of the prototype, and then BH will be the breadth of the BP will be the breadth of the prototype. So let us having the ratios LM by LP, BM by BP, HM by BP will be equal to LR. So LR is called the scale ratio or the scale factor. Okay, so for example, if I do the model in 10 meter and my prototype will be 20 meter means my scale ratio is of 0.5. So likewise, area ratio for area ratio will be the square of our scale ratio, and the volume ratio will be the cube of our scale ratio. So next one is the kinematic similarity. So in kinematic similarity is the similarity of motion. So if at the corresponding points in the models and in the prototype, the velocity or acceleration ratios are same, and the velocity or acceleration vectors point in the same direction, the two flows are said to be kinematically similar. So first thing we have, for example, I have a two pipe flow, one in model and another one in prototype. Okay, so I have point A and then point B. So likewise, point A, point B. So this is model and this is prototype. So at point so 1 and 2. So at velocity of fluid at point 1 in the model is V1 m, and then the velocity of fluid at point 2 in the model is V2 m. And acceleration of fluid at point 1 in the model is A1M and then A2M. So likewise, the prototypes we will replace by the M by P. So what we have to for the kinematic similarity, we have to find out the velocity ratios and then acceleration ratios. Okay. So the directions of the velocities in the model and prototype should be same because the velocity and the acceleration are the vector quantity. So the directions also should be same. So that is very important. The geometric similarity is a prerequisite for the kinetic similarity. So you cannot able to directly go for the kinetic similarity without checking the geometric similarity. Then next we will move on to the dynamic similarity. So, in dynamic similarity is the similarity of forces. So, kinematic similarity is similarity of motion. Dynamic similarity is the similarity of forces. The flows in the model and in prototype are dynamically similar if at all the corresponding points, identical types of forces are parallel and bear the same ratio. In dynamic similarity, the force polygons of the two flows can be superimposed by change in force scale. For example, inertia force of the model and then viscous force of the model and then gravity force of the model. So correspondingly prototypes. So we have to find the force ratio. The directions of the corresponding forces at the corresponding points in the model and prototype should also be the same. So why we have to deal with the directions? Because force is also a vector quantity. So next we will move on to the forces influencing the hydraulic phenomena. So what are the forces involved in the hydraulic phenomena we will study. Then we will move on to the numbers, that is dimensionless numbers. Okay. So first one is the inertia force. So inertia force, it always exists in the fluid flow problem. Okay, it is equal to the product of mass and acceleration of the flowing fluid and acts in the direction opposite to the direction of acceleration. So that is the inertia force. So that will also F is equal to mass into acceleration, but the direction will be the opposite to the acceleration. The next, viscous force. This is present in fluid flow problems where viscosity is to play an important role. It is equal to the product of shear stress due to viscosity and surface area of the flow. The next one is the gravity flow. Sorry, gravity force. It is present in case of open surface flow. So in most of the open surface flow, gravity forces will be available. It is equal to the product of mass and acceleration due to gravity. So here, the difference between the inertial force, that is the M into A, here gravity force M into G. And pressure force, this type of force is present in case of pipe flow. It is equal to the product of pressure, intensity, and cross-sectional area of the flowing fluid. So force per area, that is the pressure. So if we multiply with the area, we can able to get the pressure force. The next, surface tension force, it is equal to the product of surface tension and length of the surface of the flowing fluid. So surface tension we will mention in sigma. So F surface tension will be equal to surface tension into the length of the fluid. The next, elastic force, it is equal to the product of elastic stress and area of the flowing fluid. So this is that is the elastic force. So these are the forces influencing the hydraulic phenomenon. So next we will move on to the dimensionless numbers. So this is very important in fluid mechanics. Dimensionless numbers, also called the non-dimensional parameters, are obtained by the dividing the inertia force, which always exists when any mass in motion. Therefore, by viscous force or gravity force or pressure force or surface tension force or elastic force, the important dimensionless numbers are totally five dimensionless numbers. So based on these numbers, we have some modeling also. So we will see in the upcoming slides. So first we will study about the numbers. First one is the Reynolds number, second Ford's number, and Euler's numbers, then Weber's numbers, and then Mach number. So first Reynolds number. So Reynolds number is defined as the ratio of the inertia force to the viscous force. So Reynolds number is the ratio, the inertia force to the viscous force. So to find out the inertia force, that is nothing but mass into acceleration. So for mass of the fluid, we can able to find out from the density formula, because density is nothing but mass by volume. Therefore, if you multiply with the density with the volume, means we can able to get the mass. So rho into V, that will be the first one. Rho into volume into velocity divided by time is the acceleration. So that rho rho and then area into velocity, that means we can able to get the volume flow rate, then multiplied with velocity. So that is rho into a into v square. This is the inertia force. Then viscous force, that is nothing but shear stress into area. So for tau we have the formula of mu du by dy into area. So for du by dy we have the velocity and then length. So once we substitute here, Reynolds number is the rho into V into L divided by mu. So in case of pipes, so if it is in the case of pipe means we have to take in the diameter, so that this equation Reynolds number will be equal to VL divided by V. This V is the rho by mu is the kinematic viscosity. So if you know only the dynamic viscosity means you will go with this formula. If you know the kinetic viscosity, you will go with this formula. So in case of the flow inside the pipe means the formula is VD by small v. Reynolds number signifies the relative predominance of the inertia to the viscous force occurring in the flow systems. This number is taken as the criterion of dynamic similarity in the flow situations where the viscous force predominate. Example, motion of submarine completely underwater, low velocity motion around automobiles and aeroplanes, incompressible flow through pipes of smaller sizes, and flow through low speed turbo machines. Next one is the Frod's number. So Froid number is the ratio of inertia force to the gravity force. So once again, the inertia force is rho av square. For the gravity force, F into g, mass into g, acceleration due to gravity. For mass, rho into volume into gravity. So that for volume, rho L cube dot g. If we take L square as the area means rho A into L into G. So therefore, Froid number is V divided by root of L into G. So once we divide this one, we will get this one. So Frod's numbers governs the dynamic similarity of the flow situations. So Reynolds number governs the wait. Reynolds number also governs the dynamic similarity. This also governs the dynamic similarity of the flow situations where gravitational force is more significant and all other forces are comparatively negligible. Examples being flow over notches and wires, flow over the spillway of a dam, flow through open channels considering waves and jumps, and motion of ships in rough and turbulent sea. Next one is the Euler's number. So it is defined as the square root of the ratio of inertial force to the pressure force. So once again, if we simplify these terms, we can able to get the Euler number will be equal to V divided by root of P divided by rho. So Euler number will be root of V divided by root of P divided by rho. The Euler number is important in flow problem situations in which pressure gradient exists. Examples are discharge through orifices, tees and sluices, pressure rise due to sudden closure of valves, flow through pipes, and water hammer created in penstocks. The next one is the Weber's number. It is defined as the square root of the ratio of inertia force to the surface tension of the force. So once we solve this, we can able to get V divided by root of sigma divided by rho into L. This number assumes importance in the following situations: so capillary movement of water in soils, flow of blood in veins and arteries, and liquid atomization. So this number will be useful for these types of problems. Then next we will move on to the Mach number. So with the help of this Mach number only, we can able to classify that whether the given flow is a incompressible or compressible flow. So the formula for this is inertial force to the elastic force, ratio of inertia force to the elastic force. The Mach number B by C, where V is the velocity of the fluid and then C is the velocity of the sound. The Mach number is important in compressible flow problems at high velocities, such as high velocity flow in pipes or motion of high speed projectiles and missiles. So these are the numbers. The next we will move on to the model laws. So based on the numbers, we have five model laws that are Reynolds Models law, and then fraud model law, and then Euler model law, then Weber model law, and then Mach model law. To ensure the dynamic similarity between the model and prototype, it is necessary that the ratio of the corresponding forces acting at the corresponding points of the model and prototype be made equal. It implies that the dimensionless number should be same for the model as well as the prototype. So in all the types of laws, for example, Reynolds model law is nothing but Reynolds number of the model will be equal to the Reynolds number of the prototype. So that's the law. So likewise, fraud model law also, Euler model law, and then Weber model law, and then Mach model law. So we will see these things. It implies that dimensionless numbers should be same for the model as well as the prototype. This condition is difficult to be satisfied for all dimensionless numbers. Hence, models are designed on the basis of the force which is dominating the flow situation. The laws on which the models are designed for dynamic similarity are called model or similarity laws. So this is the definition. The laws on which the models are designed for dynamic similarity are called the model similarity laws. So we will see one by one. So let us take first one, Reynolds model law. So in flow situation wherein in addition to inertia, viscous force is the other predominant force means the similarity of flow in the model and its prototype can be established if Reynolds number is same for both the systems. This is known as Reynolds law, and according to this law, Reynolds number of the model will be equal to the Reynolds number of the prototype. The formula for the Reynolds number is rho V L divided by mu. So M means model and then P means prototype. So we will see some derivations. So if we rewrite this one, uh, here it is nothing but just we will divide equating into one side. So if we equating into one side, what will happen is um, P sorry rho of the density of the prototype divided by density of the model multiplied with the volume of the prototype divided by volume of the model, and then length of the prototype into length of the model by length of the model, and then 1 divided by mu rho and then mu m equal to 1. So what I replace this for the density of the prototype divided by density of model will be with the help of rho, or that is ratio, that is scale ratios, or the various quantities which subscript represents the corresponding scale ratios, that is density scale ratio, and then volume scale ratio, and then length scale ratio. So this is for the Reynolds model. So also for the time scale ratio, TR will be equal to LR divided by VR, because velocity will be equal to the length divided by time. so that we will replay change like this one. For acceleration, we are divided by TR. For force scale ratio, mass into acceleration, therefore mass ratio into acceleration ratio. For mass ratio, we will have the for mass we will have the rho area into velocity. So this is the mass flow rate. So therefore, rho r AR into VR instead of AR, we will replace with the help of LR, that is the length ratio, and then multiply with the acceleration ratio. So for discharge scale ratio, discharge is nothing but rho A into VR. So therefore, rho L square and then VR. So this is the Reynolds model. So first, what we are doing is, first we will equating the equating for the conditions, that is Reynolds number of the model will be equal to the Reynolds number of the prototype. Then we will rearrange and then find the ratios, that is scale ratios for the density and then for the velocity and then the length. The next what we are doing is we are find out the time scale ratio, and then we are finding the acceleration scale ratio. So these are the general formulas. And then for the formula scale ratio, and then we are forming the discharge scale ratio. So the following are the some phenomena for which Reynolds model law can be sufficient criterion for similarity of flow in the model and prototype. So first one is the motion of airplanes, flow of incompressible fluid in closed pipes, motion of submarines completely underwater, and flow around structures and other bodies immersed completely under moving fluids. So these are the cases where we can use Reynolds model to check for the similitude. It is a dynamic similarity. The next we will move on to the frauds model. In fraud model, when the gravitational force can be considered to be the only predominant force which controls the motion in addition to the inertia force, the similarity of the flow in any two such systems can be established if the Freud's number for both the system is the same. This is known as the Freud model law. So in last case, Reynolds number for the model and for the Reynolds number of the prototype will be same, means that is Reynolds model law. So here the Freud number of the model and the Freud number of the prototype will be same, means that is the Freud's model law. Some of the phenomena for which the fraud model law can be sufficient criterion for the dynamic similarity to be established in the model and the prototype are: first one, free surface flow such as flow over spill waves, sluices, flow of jet from an orifice or nozzle, where waves are likely to be formed on the surface, where fluids of different mass densities flow over one another. So these are the fraud model law. So Vm will be the velocity of the fluid model, and Lm will be the length of the model, and Gm will be the acceleration due to gravity. So likewise, Vp, Lp, and Gp are the for the prototype. So what we are doing is to just substitute these terms in the fraud model, fraud's number. So that is Vm divided by root of Gm into Lm. So likewise, Vp divided by root of Gp into Lp. So we will derive for the Vp by Vm, which will be equal to the Lr. So here Vp by Vm will be equal to the Lr. So Lr is the scale ratio for length, and then Vp by Vm equal to Vr, that is Vr for the scale ratio for velocity. So we will derive the general thing, that is velocity scale ratio for velocity will be equal to the root of scale ratio for the length. So right now we will come into the general terms called time scale ratio. So in time scale ratio, formula is Lm by Vm. So likewise Tp by Lp, Tp equal to Lp divided by Vp. So right now if you find out the time scale ratio, so we will get Lp by Lm multiplied with Vm by Vp. So therefore Lp by Lm will be equal to Lr, and then Vm by Vp will be replaced by here Vr. So instead of Vr, we will substitute the 1 by root of Lp. Then the time scale ratio will be equal to the root of Lp. So likewise, acceleration scale ratio we will find. Acceleration will be equal to the velocity divided by time. So likewise, if we substitute all these things, we will get the acceleration ratio as 1. So and then for the discharge scale ratio, we will get LR equal to 2 pi LR power the 2.5. So once these are the simple mathematical solutions. So for this force scale ratio also, present intensity scale ratio also, we will find out the values and then energy or work and then moment scale ratios. So, so for the fraud model, we will find the other ratios too. The next one is the Euler model law. In a fluid system where a pressure forces alone are the controlling forces in addition to the inertia force, the dynamic similarity is obtained by equating the Euler number for both the model and its prototype. This is known as the Euler model law. According to this law, Euler number of the model will be equal to the Euler number of the prototype. So the formula for the Euler number is Vm divided by root of Pm divided by rho. So for the model, likewise for the prototype, Vp divided by root of Pb divided by rho p. So here, density, if we use same fluid for the model means density will be getting cancelled. So that it will become Vm divided by root of Pm equal to Vp divided by root of Pp. So this law is applied in the following flow problems. First one, enclosed fluid system where the turbulence is fully developed so that viscous forces are negligible and also the forces of gravity and surface tension are entirely absent where the phenomenon of cavitation occurs. So in these cases, we will apply the Euler model law to check for the dynamic similarity. Next, we will go for the Weber model. So in Weber model, in a fluid flow system where surface tension effects predominate in addition to inertia force. So likewise, the other numbers also here, Weber number of the model will be equal to the Weber number of the prototype. Weber number formula will be velocity divided by root of sigma divided by rho into L. So we just equate, we just apply the formula to this, then we will get this. So Weber model laws is applied in the following flow situation, that is flow over wires involving very low heads and then very thin sheet of liquid flowing over a surface and then capillary waves in channels and then capillary rise in narrow passages, capillary movement of water in soil. The next last one is the Mach model law. When in any fluid system, only the forces resulting from elastic compression are significant in addition to inertia force, then the dynamic similarity between the model and its prototype may be achieved by equating the Mach numbers, which is known as the Mach model law. So, likewise the previous things, Mach number of the model will be equal to the Mach number of the prototype. The Mach number formula will be velocity divided by root of k divided by rho. So this similitude based on the Mach model laws find application the following, that are aerodynamic testing, phenomena involving velocities exceeding the speed of sound, hydraulic model testing for the causes of unsteady flow, especially water hammer problems, underwater testing of the torpedoes. So these are the applications. The next general types of the models are undistorted models and then distorted models. An undistorted model is one which is geometrically similar to its prototype. The conditions of similitude are completely satisfied for such models. Hence, the results obtained from the model tests are easily used to predict the performance of prototype body. In such models, the design and construction of the model and the interpretation of the model results are simpler. So this is simpler, very simpler. So distorted models is one which is not geometrically similar to its prototype. So that is very important thing. In such a model, different scale ratios for the linear dimensions are adapted. For example, in case of a wide and shallow river, it is not possible to obtain the same horizontal and vertical scale ratios. However, if these ratios are taken to be same, then because of the small depth of flow, the vertical dimensions of the model will become too less in comparison to its horizontal length. Thus, in distorted models, the plan form is geometrically similar to the prototype, but the cross section is distorted. Scale effects in models. By model testing, it is not possible to predict the exact behavior of the prototype. The behavior of the prototype as predicted by two models with different scale ratios is generally not the same. Such a discrepancy or difference in the prediction of behavior of the prototype is termed as scale effect. The magnitude of the scale effect is affected by the type of the problem and the scale ratio used for the performance of experiments and models. The scale effect can be positive and negative, and when applied to the results accordingly, the correct results then hold good for prototype. Limitations of the hydraulic similitude. Model investigation, although very important and valuable, may not provide ready solution to all problems. It has the following limitations. The model results in general are qualitative but not quantitative. Second one, as compared to the cost of analytical work, models are usually expensive. Third one, transferring results to the prototype requires some judgment. The scale effect should be allowed for. Fourth one, the selection of size of a model is a matter of experience. So without experience, you cannot able to do these things. So thank you.